Dear students, welcome to Introduction to Quantum Technologies and Applications. This semester I will teach this subject. Um, in, in this first unit, it consists of Introduction to Quantum Theory and Technologies, the transition from classical to quantum physics, fundamental principles explained conceptually, superposition, entanglement, uncertainty principle, wave practical duality, classical versus quantum mechanics, theoretical comparison, quantum states and measurement, nature of observation, overview of quantum systems, electrons, protons, atoms, the concept of quantization, discrete energy levels, and why quantum, strategic, scientific, and technological significance, a snapshot of quantum technologies, quantum computing, quantum communication, quantum sensing, national and global quantum mission, and finally India's quantum mission, Europe and USA and China. And in first unit, we'll discuss about from classical to quantum physics, transition from classical to quantum physics, classical versus quantum mechanics, theoretical comparison, and fundamental principles like superposition, entanglement, uncertainty principle, and wave practical duality, and quantum states and measurement, nature of observation, quantum states and measurement. Fourth one, quantization and quantum systems, quantization, discrete energy levels, quantum systems, electrons, protons, and atoms, and why quantum, strategic importance, scientific significance, technological significance. Sixth one, a snapshot of quantum technology, which includes quantum computing, quantum communication, quantum sensing, and quantum materials. And seventh one is national and global quantum missions, India's quantum mission, and global quantum missions, including European Union, USA, and China. And the concept of quantization, discrete energy levels, quantized charges in energy. And finally, why quantum technologies enables new scientific development or discoveries, and it provides the strategic and advantages, security, and it solves the problems beyond the classical computers can solve. Now, introduction to quantum theory and its applications. The word quantum comes from the Latin word quantus, meaning how much. In modern use, it has a few specific meanings depending on the field. Quantum refers to the smallest possible discrete unit of any physical property. For example, a quantum of light is called a photon. A quantum of energy is the smallest packet of energy that can be emitted or absorbed. So, in physics, quantum is a small indivisible unit of a physical quantity. In general use, the measurable amount or a portion. In physics, a smallest possible unit of energy or matter. In quantum computing, a unit of quantum information is called qubit. Quantum technology is the principle of quantum mechanics, a fundamental theory in physics that describes nature at the smallest scales, such as atoms and subatomic particles, to develop new types of technologies with capabilities far beyond those of classical systems. What is quantum technology? Quantum technology is based on key quantum mechanical properties such as superposition and entanglement. What is superposition? Superposition is a quantum system can exist in multiple states at once until measured. And entanglement is a particles can be linked in such a way that the states of a particle instantly affects the other no matter the distance. What is a superposition? The word superposition, which is a core concept in quantum mechanics and quantum technology, a classical bit can be either 0 or 1. A qubit in a superposition can be both 0 and 1 at the same time. In a probabilistic blend represented as ket psi is equal to alpha ket 0 beta ket 1. It is known as Dirac notation or bracket notation. It can be read as ket psi equal to alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers that define the probabilities of being in each state. The ket representation of a quantum state vector, for example, ket psi denotes the state psi of a quantum system. The ket is conceptually a column vector in a complex vector space called a Hilbert space. Specific qubit basis states like ket 0 and ket 1 represents the fundamental computational state in quantum computing. The bra is the dual vector, a conjugate transpose of the ket. If ket psi is a column vector, then bra psi is the corresponding row vector with the complex conjugate elements, which is used to form inner products and projections. What is Dirac notation? Dirac notation is also known as bracket notation, is a powerful and concise mathematical notation introduced by physicist Paul Dirac for representing quantum states and operations in quantum mechanics. It simplifies expressing quantum states and computations in a way that is especially useful in quantum computing and other quantum technologies. The ket psi denotes the state psi of a quantum system. The inner product. The inner product between two states, ket phi and ket psi, is a complex number that gives the probability amplitudes of state ket psi collapsing to ket phi upon measurement. The squared magnitude gives the measurement probability. The outer product represents an operator or a matrix that acts on quantum states useful for expressing quantum gates and quantum measurements. Quantum entanglement. Quantum entanglement is a phenomena in a quantum physics where two or more particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are, even across vast distances. When two particles like photons, electrons, or protons interact in certain ways, their quantum states become correlated. After they separate, measuring one particle's state, say its spin or polarization, will instantly determine the state of the other, regardless of the distance between them. Photon, it refers to a particle of light or a quantum of electromagnetic radiation. A photon travels at the speed of light. A photon is a quantum of a light. Matter. Matter is anything that has mass and takes up space. Everything we see and touch is made up of matter. Example, water, air, wood are all forms of matter. Atoms. An atom is the smallest unit of matter that still retains the properties of an element. Everything around us is made of atoms. Example, all matter is made up of atoms. Electron. An electron is a tiny particle with negative electric charge found in atoms and responsible for electricity. Electrons revolve around in the nucleus of an atom. The main branches of quantum technology has mainly four branches. One is quantum computing, second one is quantum communication, third one quantum sensing and meteorology, fourth one quantum simulation. Quantum computing. Quantum computers utilizes qubits or quantum bits instead of classical bits 0 or 1, capable of solving certain problems exponentially faster than classical computers. The key players in this quantum computing are IBM, Google, Microsoft, IonQ and Rigetti. Quantum communication ensures secure data transmission using quantum cryptography, example quantum key distributions. Quantum sensing and metrology provides ultra precise measurements of time, gravity, magnetic field, etc. Quantum sensors can be used in navigation, geological exploration, and medical diagnostics. quantum simulation simulates complex quantum systems that are difficult to model with the classical computers, useful for understanding materials, drug discovery, and high energy batteries. Applications of quantum technology. Uh, Quantum technology has so many applications, which including cryptography and cybersecurity. Quantum key distribution allows unbreakable encryption methods, potential to secure national defense, financial transactions, and personal data. And second one is healthcare and life sciences, quantum simulation for drug discovery and protein folding, and financial modeling, quantum algorithms for portfolio optimization, risk analysis, and fraud detection. Artificial intelligence and machine learning, quantum enhanced machine learning offers faster training and data processing. Fifth one is climate modeling and material science. Simulating atomic scale process helps develop new materials uh, for batteries, solar panels, and carbon capture. Navigation and positioning. Quantum gyroscopes and accelerometers for GPS-free navigation, submarines or spacecrafts. Current challenges and future outlook. Scalability. Building reliable, large-scale quantum systems remains a major hurdle. Error correction. Quantum systems are highly susceptible to noise and decoherence. And standardization. Common protocols and infrastructures are still evolving. Talent gap. A growing need for skilled professionals in quantum science. Now, the transition from classical to quantum physics. The classical physics, Newton mechanics, Maxwell's equations explain most macroscopic phenomena. However, it fails at atomic and subatomic scales. Problems like blackbody radiation, the photoelectric effect, and atomic spectra lead to the development of quantum physics. Quantum theory emerged as a new framework to describe nature at these scales where energy and matter behaves differently. Example, in the photoelectric effect, increasing the brightness of light doesn't always eject electrons, only light above certain frequency does. This leads to Einstein's quantum explanation in photons. Coming to the blackbody radiation, a classical physics could not explain the observed spectrum of radiation emitted by a black body, which led Max Planck in 1900 to propose that electromagnetic energy is quantized, emitted in discrete packets called quanta or photons. This marked the birth of the quantum hypothesis. Second one is photoelectric effect. Observed earlier but explained by Albert Einstein in 1905, the photoelectric effect showed that the light must behave as discrete energy packets or photons to eject electrons from a metal surface. The kinetic energy of these ejected electrons depends on the light frequency, not its intensity. Contrary to classical wave theory predictions, Einstein's explanation provided strong evidence for quantization of light and helped establish quantum theory. Atomic spectra. Observations of discrete emission lines from the atom like hydrogen indicated that the energy levels of electrons are quantized. The quantized model of the atoms incorporated quantized electron orbits further leads to quantum ideas. All incident radiation is absorbed by the black body, but emitted radiation is only a function of temperature. Here is a photoelectric effect. The electromagnetic radiation that incident on the metal surface, it emits photoelectrons. Fundamental principles of quantum technology. First one is superposition. A quantum particle can exist in multiple states at the same time. This is called superposition. A quantum bit in a quantum computer can be in both 0 and 1 states at the same time. The quantum state can be represented by a ket psi is equal to alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers with the probabilities of the ket 0 and ket 1, that is alpha square plus beta square is equal to 1. Entanglement. Two particles become entangled if the state of one instantly affects the state of the other, no matter the distance between them. Examples: if two photons are entangled and one is measured to be vertically polarized, the other will instantly be horizontally polarized even if it's kilometers away. The uncertainty principle. Heisenberg's uncertainty principle says that we cannot simultaneously know a particle's position and momentum exactly. For example, if you know an electron's position very precisely, that is inside a tiny box, we cannot know its momentum. It might be moving rapidly or slowly, and we cannot predict both exactly. Wave particle duality. Quantum objects can behave both like particles and waves depending on how we observe them. In the double slit experiment, electrons fired one at a time still create an interference pattern like waves until we observe which slit they pass through. Then they behave like a particles. Classical versus quantum mechanics. Theoretical comparison. Key points. Basics of computing. Large-scale multi-purpose computers based on classical physics. Quantum computing. High-speed computers based on quantum physics. Information storage. Bit based using voltage or charge. Quantum bit based using electron spin or polarization. Bit values. Bits having a value either 0 or 1 can have a single value at any instant. Qubits have a value of 0, 1 or sometimes linear combination of both, a property known as superposition. Number of possible states. The number of possible states is 2, which is either 0 or 1. The number of possible states is infinity since it can hold combinations of 0 or 1 along with some complex information. Output. Deterministic. A repetition of computation on the same input gives the same output. But on quantum computing, the output is a probabilistic. Repetition of computation on superposed state gives the probabilistic answer. Gates used for processing. The logic gates and or not gates are used in classical computing. Logical gates like poly x, y, z, Hadamard gate, CNOT gate are used. Operations. The operations are Boolean algebraic operations. The operations in quantum computing, the operations use linear algebraic and represented with unitary matrices. Classical versus quantum mechanics. Classical mechanics treats motion and energy as continuous, and systems evolve along smooth trajectories in space and time. And quantum mechanics, however, reveals that the energy is quantized or discrete energy levels are allowed. Quantum states and measurement. What is a quantum state? A quantum state describes the complete information about a quantum system like an electron, photon or proton or atom. It is usually represented as a wave function in a quantum mechanics. It tells you everything that can be known about a particle, such as its probability of position, momentum, spin, etc. Mathematically, a quantum state is a vector in a Hilbert space. In direct notation, it is written as ket psi. Example: a photon polarized horizontally, that is ket h. A qubit in superposition state, a ket psi is equal to alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers, satisfying the condition modulus of alpha square plus modulus of beta square is equal to 1. And what is quantum measurement? Quantum measurement in quantum mechanics is not like classical measurement. It has special rules. Measurement collapses the state. Before measurement, the system exists in a superposition, or multiple possibilities. When you measure it, the wave function collapses into one definite outcome. After that, the system behaves classically until disturbed again. Second, outcome is probabilistic. The result of the measurement is not deterministic. Each possible result has a probability given by the square of the amplitude, that is p is equal to modulus of alpha square. Die in a box analogy, the quantum mechanics can be understood. Uh, Die rolling unseen inside the box. It shows that the superposition system exists in combination of possible states. In a die, the possible die faces are 1 to 6. The eigenvalues possible measurement results. Opening the box to look in quantum mechanism, it is like the measurement interacting with the system to get the result. Die suddenly shows one fixed number. It represents the wave function collapse. System picks one definite state. Now, rules of the die roll, fair or unfair die, the probability amplitudes wave function determines chance of each outcome. Seeing the same number if checked again immediately, repeatability postulate. Once the measured, the state stays the same till it is measured. Shaking the box again before looking, the new state preparation changes into the superposition state. For example, spin measurement. An electron spin can be up or down along a along a direction. Before the measurement, the ket psi is equal to 1 by square root of the upspin or the downspin. After measurement along z axis, it becomes either the upspin with 50% chance, downspin with 50% chance. The momentum is the quantity of motion an object has. It depends on how massive the object is. Momentum is equal to mass into velocity, that is equal to m into v, where p is the momentum, m is the mass, v is the velocity. Nature of observation in quantum mechanics. In quantum physics, the nature of observation is fundamentally different from classical science. It's not just about looking. Observation changes the system being observed. What does observation mean? In quantum theory, observation or measurement refers to interacting with a quantum system to extract information like the position, momentum, or spin of a particle. But unlike in classical physics, this interaction affects the system in a fundamental way. Example, double slit experiment. When electrons are fired through two slits, if not observed, they create an interference pattern like waves. If you observe which slit they go through, the interference disappears, they act like a particles. The concept of quantization, discrete energy levels. What is quantization? In quantum physics, quantization means that certain physical quantities like energy, charge, angular momentum can take only specific discrete values, not a continuous range. For example, hydrogen atom. In the hydrogen atom, the electrons cannot orbit at any distance from the nucleus. Instead, it occupies quantized energy levels where n is equal to 1, 2, 3 and so on. When the electron jumps between the levels, it absorbs or emits energy as photons. The Tn is equal to minus 13.6 electron volts per n square. This explains the line spectra of elements, that is Balmer series for hydrogen. More examples, electron in atom The quantized properties, energy levels, photons in a laser, discrete energy packets, quanta, particles in a box, quantized momentum and energy, light comes in photons with E is equal to hf. Why quantum technologies? Highlighting its strategic, scientific and technological significance with examples. For each, we'll see here. First one is the scientific significance. Quantum mechanics fundamentally challenge how we understand the universe. The key concepts: superposition, entanglement, and uncertainty principle. Superposition means a quantum system can be in multiple states at once. Entanglement: two particles can be connected over long distances. Uncertainty principle says that we cannot precisely know both position and momentum at the same time. And the photoelectric effect is the emission of electrons from the surface of a metal when light of a certain frequency or light falls on it. These emitted electrons are called photoelectrons. The photoelectric effect, explained by Einstein using a quantum theory, classical physics failed to explain why light below a certain frequency does not eject electrons, but quantum theory did, earning Einstein's the Nobel Prize. Atomic model: Niels Bohr's model of the atom could not work without the quantum energy levels. Now, technological significances. Quantum mechanics is being applied to build radically new technologies. Quantum technologies, quantum computing, solve problems beyond classical computers. Quantum communication enables hack-proof data transfer. Quantum sensing allows ultra-precise measurements. Examples: quantum computers. Google Sycamore quantum computer solved problems in 200 seconds that would take a classical supercomputer 10,000 years. Quantum key distribution. China's mucus satellite transmitted entangled photons over 1,200 kilometers for secure communication. Quantum sensors used for underground mineral detection and and independent GPS independent navigation by detecting gravitational variations. Now, strategic significance: the quantum technologies affect national security, cyber security, and economic power. The key strategic areas are cyber security. Quantum computers threaten existing encryption standards, example RSA and ECC. Defense: quantum radars can detect stealth objects. Quantum navigation works without GPS. Economic superiority: quantum innovation drives future industrial competitiveness. Examples: USA National Quantum Initiative invested 1.2 billion uh, in tech, billion dollars. Technological giants like IBM and Microsoft lead in quantum R&D. China leads in quantum communication and has built the world's longest quantum network. India launched the National Quantum Mission in 2023 with 6,300 crores for developing the quantum computing, quantum communication, quantum sensing. Military use: quantum magnetometers and gyroscopes are being tested for submarines and aircraft to operate without GPS. These are the main aspects, significance, and examples. Scientific: explains atomic and subatomic behavior, foundations for the modern physics. Photoelectric effect, Bohr's atom models. Technological significance: enables new tools in computing, sensing, and communication. Google Sycamore, Messier satellite, quantum gyroscopes. Strategic significance: determines future cybersecurity, military technology, and economic leadership. National Quantum Mission, US, China, Europe, and India, the quantum key distribution and quantum encryption. A snapshot of quantum technologies: quantum computing, quantum communication, and quantum sensing. The quantum technologies leverage the principles of quantum mechanics like superposition, entanglement, and quantum tunneling. Quantum computing. Quantum computing uses qubits instead of classical bits. A bit can be in a superposition of 0 and 1, allowing quantum computers to perform parallel computations. It is all about qubits, quantum gates, quantum circuits, and algorithms such as Grover's and Shor's that outperforms the classical solutions. The key principles are superposition, entanglement, and quantum interference. The applications are quantum cryptography, breaking classical encryption algorithms like RSA using Shor's algorithm, optimization, solving complex problems in logistics and finance, drug discovery, simulating molecular interactions quickly and accurately, like IBM and Google Quantum AI, machine learning, speeding up of learning algorithms with quantum error corrections and processing, and quantum communication. Quantum communication uses quantum states like the polarization of photons to transfer information securely. Key principles. Quantum key distribution using entanglement ensures that any eavesdropping attempt disturbs the system, making it detectable. Applications. Secure communication networks, unhackable, satellite based quantum internet, quantum teleportation of information, not matter. Examples are China's Mischief satellite, world's first quantum communication satellite, demonstrated secure quantum key exchange between two ground stations. India's quantum key distribution test between DRDO and IIT Delhi. Quantum sensing. Quantum sensors exploit quantum properties to detect and measure extremely small changes in the physical quantities like time, magnetic fields, gravity, or acceleration. Key principles. Use of superposition entanglement in atoms, ions, or protons to enhance measurement sensitivity. Applications. Navigation without GPS using quantum gyroscopes. Medical imaging with ultra high resolution. Example using quantum enhanced MRIs. Geological exploration detecting underground structures with quantum gravimeters, atomic clocks. Most precise timekeeping devices for GPS and scientific research. Examples quantum gravimeters developed by companies like QCTRL and Mucians for underground voids and oil reservoirs. Optically pumped magnetometers used in brain imaging to detect tiny uh, blood clots produced by neural activity.